All right. So hey everyone. So welcome back. So I hope everyone has. I hope everyone's turned in their data collection report. A few of you told me that the fifth part, where I asked you to simulate or to think about generating, other data, that you were confused and you had to think about that. And the response to that is good. The intent was to make you try and actually have to think about something. So that's normal. Well, I don't know if it's normal in the general population, but hopefully it's normal for this class that you have to do some thinking. Okay, so what's on par for today? Let's see. So I posted the next assignment for clustering. How many people have taken a look at the assignment already? I know a few of you have. Okay. So it's due. Let's see. It's already due next week, Wednesday. So is this? So the following Monday is going to be the first quiz, and I'll talk more about that next week. And then the week after that is going to be the break, and then the intermediate report is due right after break. I'd rather you kind of this is probably one of the first three homework assignments are going to be a little bit more work intensive than the ones that come at the end of class, at least for most people. So I want you to get those done out of the way and start really going on the project. But I know the deadline's coming up quick. So do people think it's too soon? We could move it back, but I don't want it to interfere with like your quiz and you're working on your project. So any thoughts on that? Okay, so then I'll probably leave it in place. We still have 2 weeks, or at least a week and a half to do it. It should be fine. So I know most of you do it in the last few days anyway. So, right? Yeah. Okay. That's when I get most of the questions about it. Okay. So we'll keep that due then. Okay. So we were talking about clustering, and we're pretty much done with the clustering section of class. We'll come back and talk about something similar to clustering in the section on graphs at the last section, and we'll also talk more about these ways of thinking about the eigenvalues and stuff when we talk about regression and going up to high dimensions. And we'll build some more intuition about what's going on there as well, and in a different form, but we'll make sure to relate that back to the eigenvalues. So if that was spectral clustering was kind of mysterious, well, that's not uncommon, but hopefully we'll see it in a different form again and help make it a little bit so it's a little bit less mysterious. Okay, so then today and this week we're going to focus on finding frequent items and frequent item sets this week, and in particular, these techniques will be kind of tailored towards kind of really large data. So we'll be looking at the problem called frequent items, and so this, there are other ways you could look at this, but we're talking about very large data. And so the clustering techniques, some of them took, in the number of data points, they took n squared or n cubed time. That's not at all feasible. We'll talk about techniques where maybe you don't want to do any more than just basically read the data, right? So you don't want to make iterations over it. You just want to kind of read it very quickly and get some basic summaries out of it. And so kind of before we get into this, let me give a kind of a high-level picture of this whole area of talking about really large data. So before we had talked about this idea of you have these data points, and maybe they're IID from some sort of distribution, and I said maybe there's some parameters there's some parameters that describe this distribution. Maybe this is like the mean and variance from some Gaussian or something, and there's some underlying process which is describing this, and there's some kind of specific parameters. There's a lot of the field of of if you think of something like, if you'd call something like computational statistics or just statistics, it may be kind of learning these parameters that describe some distribution or understanding them. But in data, it's, you don't necessarily want to make an assumption that there is some underlying process like this, or maybe you do, but maybe it's less clean. And instead, you'd say you have some, this was as IID, these are all the same, and this end up giving you this, you have x1 through x2. This gives you this set. Instead, we want to take this data, which was equal to x, and create some other sort of summary of this data. Okay, and it's going to act like these parameters. It's going to be a very concise way of representing it, but the summary will have some trade-off, some trade-off between the error versus the size. So if we can have a very small error, then if we keep the whole data set, then we're not going to have any error. But if we want to kind of keep a summary of this, which is much smaller, we may introduce some error, and kind of understanding this trade-off. So we're going to create this summary of the data set, very large, but bring it down to a very small, much smaller representation. And it could be like thinking about these parameters, but this is more general. It's not making this IID assumption necessarily, and it's a more general way of thinking about this. But if you've seen this idea of statistics where you're trying to estimate these parameters, this in some way is a way of generalize this, where you have data and you want to create this summary. Okay, so that's kind of the high-level view. The other thing is that we're going to be talking about a specific large-scale setting called streaming. Okay, and so the idea of a stream is that your data, often we'll say your data may be something like the set A, and its elements let's see, A1, A2, up to AM. Okay, you're going to get these elements, and the idea is that this stream is very, very large. So it could be that this, I was talking to some people before class, their project, they have like 800 gigs of data, or maybe was it 800 gigs? Yeah, so 800 gigs of data. And so at that point, to do some analysis, you can't fit this in the memory of your computer. You can really only kind of, you can maybe read through this data once, right? And you want to create some analysis while just reading through it once. Another thing is this data is so big, it's probably generated by some process, and that process is going to keep coming, right? You're going to keep getting more and more data. And as you keep this data, you don't want to wait till the data stops coming to do your analysis. You want to always have some analysis going. And so you're going to think about there's this whole stream, but you're at this part of the stream right now. And so you can see this data from here, from the start up to this point, and you want to have an analysis, and we'll call this is maybe data point AI, and this is data set capital AI, and you want to do some analysis on this, right? So I want to get some summary, say SI, out of here. So this same idea of taking data, bringing it down to a small summary, and at every time point, I want to have a summary of what's going on in my data. Okay, and I don't want to wait till the end because there may never be an end, and I want to keep maintaining this as I'm going. Okay, and so one of the ways that this sort of analysis was first important was when you're trying to think of what you can do if you're sitting on a router on the internet. Okay, so this router, how they, if you know about how the internet works, you have these routers sitting, someplace, and you have data coming in from these other routers, and then the router says, well, it needs to go out to these other guys. And all it does is it reads this IP packet, it looks at the header, and then it sends everything on, and it eventually gets to where it needs to go. And it's doing this all day. There's so much information, it's just passing through this router. They're not keeping anything on here. And so, but you may want to keep some summary, say, over this day, what happened on this router. Right? They're kind of just an enormous amount of data which is going through here, and you can't store it. You can just kind of see it as it's going through and hope to kind of keep some kind of have some basic summary of what's going on. And in particular, what's interesting to think about is, you know, you're just looking at the header of some packet, right? So you get, you know, this part, maybe the actual stuff you're sending. Maybe this is like a video or a web page or an email, but you have the header up here, and one of the main things up here is the IP address, right? The IP address is going to be is going to be 32 bits. Okay, so 32 bits describes where it came from and where it's going to, and this is what the router needs, aside from some other information. And kind of one of the major issues with these routers is if people are doing something nefarious, they're going to be doing like a denial of service attack. So if that means that they're routing a lot of information just to one of these IP addresses over and over again. And if you're a router, you want to say, okay, this is not normal. I want to alert it, or maybe I would block everything going to the IP address for now and cause some other, that prevents some other part of the system from going down, right? Or I would put a special filter on these because this IP address said, well, I'm getting a lot of bad stuff coming from this one guy over here. So if I get an IP address coming from here out to here, I want to block it because that's something bad going on. And eventually there's protocols that allow you to trace it back, these bad, back to the source, and you can block them, okay? But to do that, you kind of need to know that this IP address has been seen a lot, okay? But the challenge is, you know, there are 32 bits to describe it, so I can't just keep track of which IP addresses I've seen a lot. There are 2 to the 32 possible IP addresses. Well, you know, there's some special characters, so it's not quite this big, but it's a really big number. I can't keep an array of size 2 to the 32 on the router. I probably can't even keep a list of all the ones I've seen in a day or in an hour, right? So I don't want to do this. I don't want to kind of keep track of all of the IP addresses, but I want to know which ones are having a lot of stuff routed to them, and maybe which ones are having a lot of stuff routed from them. So I want to keep track of these really kind of common IP addresses. And these are, and we'll describe this more formally, but these may be called the heavy hitters. Okay, so these are the IP addresses or the elements which are occurring very frequently. Okay, and so, you know, so I'll define and I'll spend this lecture specifically on this problem of the heavy hitters. And this is one example of the ways you can take this large data set and create some really concise summary that really tells you what you need to know. It's a useful example for a few reasons. One is, you know, this isn't just the IP address application that it's useful for, although this is was, I think, one of the early ones and is a really useful case of it. But it can come up in other ways, like you're trying to keep track of, say, just the most important K-grams which are coming through in tweets. As you're seeing, this is maybe a feed of all of Twitter. You're looking at, you're trying to make a scan over some other document, like some, you know, most common words in the English language, or, you know, so for some very simple sort of task, you kind of just want to keep track of which ones are the most frequent items. These are the things that tend to be the most interesting going on. So I want to keep track of just which ones are frequent, and then a counter for each of these to see how many times they actually come. Okay? The like the so another reason why we look at this problem is that there are actually a handful of different techniques for creating summaries of this type, and they kind of use like a whole different range of techniques. And we're gonna today we're gonna talk about two of them. One uses a clever way of counting and bookkeeping. And this is interesting because it'll actually come up later when dealing with very large matrices. It'll use a very similar technique, but extend it to be into these more complex data. And another one is using kind of these hashing and randomized techniques that we kind of started to talk about earlier. And you'll see that both of these techniques can kind of solve the same problem and have different advantages and trade-offs. Okay, so so you'll get a taste of what sort of things you can do for these family problems. But this is just one sort of thing where you have data and you want to create a summary. And so even though this will be kind of fairly simple, the summaries we get, you can kind of layer stuff on top of it and do more interesting things. Okay, so kind of before let me define streaming, kind of this version of the stream problem, a little bit more formally. So we'll think of, we'll have A1, A2, we'll have, let's see, this will be AI up to AM. So we'll think of this as the stream, and we're currently at this spot in the stream. This is AI. So, it goes up to, maybe we'll talk about the size of it in terms of this value M. Okay, and we're going to say that each of the elements AI is going to come from some sort of, they're all going to have the same pattern. And, generally we'll say that these come from some universe of size N. Right, so remember back to the first lectures, we said elements came from, and then you can map these to numbers, 1 through N. But you can think of this as being the, this could be space of IP addresses. These could be like the words, on Twitter, and so forth. Or maybe even you think they're duplications of certain tweets, right? Or maybe it's the hashtags on Twitter or something like that you're keeping track of. Okay. Or maybe you're monitoring a web page, and these are kind of a certain pattern of interaction on web. But we'll say that these are each going to be distinct. Now maybe you can associate some together. That's maybe that's a post-processing, maybe a pre-processing step. Okay. And we're going to say that both N and M are very large, such that if you're on a router, then they're too big to store something of size N or M on your machine. So something like O of N, or should be omega. So omega of N or omega of M space is too much, right? So I can't keep a counter for every IP address. I can't keep even one bit of information for every element I've seen in the stream. Okay, I don't want to store all of Twitter. Even for a long time, Twitter even wasn't storing all of Twitter, right? There was so much going on there, and a router isn't storing all of these IP addresses. So I'd rather work in, my goal is something where the space looks something like the O of log of N or log of M. Okay? So like log of N, if this was a space of IP addresses, log of N would be like 32 bits. Right? So this is reasonable. Log N is 32 bits. 2 to the 32 is unreasonable. Right? So I can label each of these things I've seen with 32 bits, right? But I can't list them all out, right? And M, this is like keeping a counter of how many I've seen. And again, log the number of things I've seen. That's what I need to count how many things I've seen, right? So this is counting how many I've seen, and this was a label. Okay, so I want to keep, so I can think of keeping these labels and these counters. Okay, and so then to find this, the heavy hitter problem, and more generally the frequent items problem, I can think of something called the frequency. I'll use a J for this, I think. And the frequency is defined as, I'll write this out and then make sure we follow. So okay, so this is the size, so the cardinality. So these vertical bars tells me the size of a set. The curly brackets tell me a set. And I'm saying all elements in the stream such that this means such that, right? So such that this value of the element is j, right? So if I'm looking at one IP address, that takes the value j. This is the frequency of that IP address, how many times it came. So this could be the number of times IP address j came. Okay, and so the frequency approximation so that would be to come up with some counter fj. We'll call this fj hat. So fj minus fj hat, I want this distance to be bounded. I want for all of these counters that this to be close. I want to come up with an approximation here. Okay, and I want to say that this difference is going to be less than some parameter epsilon times n. And this is usually write it in this form because for a value of epsilon between 0 and say 1/2, you can generally get some bound like this, right? So epsilon is usually much smaller than 1/2. So you can think of epsilon as being 0.01, something like this. Right? So this would be an example. But you'd be in terms of n, and again, n is going to be actually this will be m often. This case. So epsilon times m. So the worst case is making epsilon greater than 1 would make sense because I'm at most going to have m counters and items with any single value, right? So making it greater than 1 doesn't make sense. So I want to make it some small fraction of that. So so then this epsilon is like the fraction of items that have this value. So I'm off by, this would be 1/10 of 1% if I set epsilon to this value. And so if I'm talking about like this example with IP addresses and these denial of service attacks, it could be that the denial of service attack really is not that big a deal unless it reaches like 1% or maybe 5% of all the data going through that router. So if I'm trying to estimate something that, say, I want to know if it's above 1% and I'm off by 1/10 of 1%, well then that's okay. Right? If I care about if it's above 5% and I'm off by 1%, well, that's probably also okay. Right? So so then the heavy hitters problem is generally defined to is to find. Let me write this up here. Okay, so the heavy hitters problem is to find all j in n such that fj is greater than some phi m, and this would be like a phi heavy hitters problem. Okay, so I set some value, say this is 5% or 1%. I want to find all IP addresses that more than 1% of the traffic is routing towards these IP addresses. Okay, and so often, I want to find all that this is true, and often I want to allow an approximation of it. So I'll put this this phi and epsilon in the definition, and then I say I also want so I want all of these, and I want if fj is less than or equal to phi of m minus epsilon m, then of these I want none. And then if fj, let's write it this way. If I say phi of m minus epsilon m is less than or equal to fj is less than or equal to phi of m, then these are a maybe. I can sometimes return these values j, but I don't have to. If it's greater than this threshold, I always want to find them. If it's in here, then I can make some mistakes. That's okay. If it's less than this, I don't want any of these false positives. I don't want to chase down a bunch of things that were really just noise. Okay, so this is kind of formally what the heavy epsilon phi heavy hitters problem is. Okay, so is it possible? So let's say that that the phi here is going to be 5%, right? Is it possible I'm still going to be returning so many of these things that it's going to take too much space, right? That I have this thing that this much space is too much, right? Am I going to potentially be returning, there could be a lot of things that are very popular, right? Can I possibly return, like omega n different IP addresses? If n is really big, is that possible? This is the part where I pause to see if people are still following, okay. So what would happen if I had 100 different IP addresses that were each getting 5% of the traffic? That sounds like a really bad problem, right? Is that problem possible? So let's say, let's put this down here. So let's say I looked at, this. I have all of my traffic here. This is 0%. This is, 100%, and I haven't told you what any of it is yet. And so if I say something is bad if it takes more than 5% of the traffic, okay, so let's say that's the first 5%. This one is bad IP address. This one is being given like a whole bunch of traffic. So this one got 5%. So now I'm at 5%. And then I say, okay, I'm going to try and put 100 of these in here. This is another 5%, another one. Keep going. Do you think I can fit 100 of them in here? No, after I do 20, this is going to be full, right? I can't have too many of these heavy hitters. So there can't be a lot of what's going on here. I'm kind of assuming, well, I guess based on this definition, I only care about the really ones that are taking a lot of the traffic. And by definition, there can only be so many of those. So I shouldn't need that much space to store all of them. I shouldn't need to keep a counter for every one of the IP addresses like this. I have this much space. I should be able to keep a lot less. Okay? Now each counter is going to take still log n or is log m space, and a label is log n space, right? But I'm going to need probably a small number of counters and labels is what I'm hoping. Because if I only care about things that even at 1%, I can't have more than 100 things that are causing 1% of the traffic. Now I may need a little bit more to make sure I get all of them, right? That seems fair, but it shouldn't be too much more than 100, right? So I should be able to do this with just a very small number of counters. I should be able to have a very small space to do this. Okay, so that kind of is believable. It seems that even though this is, could have all these crazy IP addresses coming through, if I just want to find the heavy ones, I shouldn't need that much space. And that's kind of what's going on underneath, which is the reason why this is going to work. Okay, so let's start with a simpler problem. Okay, and so this problem is called majority. Okay, so let me define this very, very carefully here. So I want to look at the frequency items, but I just want to find a really heavy hitter. So I want to say if sum fj is greater than m over 2, I want to return j. Else, if there's no j that's greater, has a frequency greater than m over 2, and remember m is the number of items in the stream, then I can do anything. I can return something, or I don't have to return anything. It doesn't matter what I do. If there's only one false positive, that's okay, right? But if something is over half of the elements in the stream, I want to find this. Okay. Now you should kind of see that this is an easier version of the previous problem. This is for really heavy hitters, right? Half of the stream. This is kind of ridiculous. But the cool thing is that I can do this with one counter and one label. And this is going to work in this streaming setting where I'm going to read through this, and I'm only going to look at one of these objects at a time. I'm going to read it. I'm going to do something to the labels and the counters I'm holding onto, and then I'm going to look at the next one, right? So I can't go back to the old things. I can't store them. I'm only going to keep stuff in one label and one counter, or I'm reading these from disk. I only want to read them from disk. I don't have random access anymore. I can't just go and look at something I forgot. If I do that, it's going to take way too long. They're stored in the cloud someplace. I don't want to go and pull them down. Right? So I want to do this with one label and one counter. Okay, so how would I do this? How would you try and keep track of a majority element in a stream with only one label and one counter? Any ideas? No idea. Okay, so what can I do? Okay, so what's the simplest thing I can do with the label? Right?
Ignore it.
What?
Ignore it.
Okay. The simplest is ignore it. All right, very, very good. I'm glad we have you in class. That's better. Ignoring is better than nothing, I guess. So okay, good.
Compare each new item with the previous largest.
Keep new item with the previous largest. So.
Just keep the largest.
So I'm keeping something, right? I'm keeping a label. I'm keeping something I've seen. Okay, good. So that's what I'm doing, right? So let's start with the first element in the stream. For A1, I'm going to set the value of this equal to my label, and then so I'm going to label something I've seen. So that's all I can do. Some element I've seen, I'm going to say I've seen that one. Right? That's better than nothing, right? Okay, so and then I can have a counter, right? So if I've seen it, if this is the first one I've seen, A1, then at this point I set the value of this. So this is an IP address equal to my label, and I have a counter. I can say I've seen it once, right? So I do this, and I set my counter equal to 1. Okay. So this is if I see one element, then this is the right thing. If I've seen one element, yes, it's greater than half the elements. It's greater than 1/2 is the frequency. So I return this label. So if I only see one thing, I'm done. Right? That's good. This works. Okay. So now, if I see a second thing, let's see. I see A2. If it's equal to this label, then what should I do? Then I increment the counter, right? So if AI, in general, if AI equals this label, then I do C++. I increment the counter. Okay, so this works. If I see something and I see it again and I have a label and a counter for it, I can increment the counter. Okay, so this part works good. What happens if I see something else? Okay, good. So I'm going to do C equals C minus 1. Okay. This works unless, what if the counter was at 1 or was at 0? What if I saw something and then I saw a whole bunch of other stuff?
Then you replace it.
Good, good. That's it. So if C is greater than 1, else there should be an if in here. If C greater than 1, then I just decrement it. Else, then I do label is equal to AI, and C is going to be equal to 1. Okay, and then this is the whole algorithm. Right, so this is, I mean, there's not a lot you can do with the counter and the label. We basically just thought through the obvious things. And this, so if you see something and you have a label and a counter, you increment the counter. You decrement the counter unless it gets too low, then you change it to this new thing. And then you know I have at least one of this new thing. And my claim is that at the end of the day, if you return the value of your label, it's going to satisfy this property. Now, this is a pretty weak property. I only care if it's really, really big, if it's over half the things that should work. If there's nothing over half, then I can do anything, right? So think of this as like I'm keeping track in like an election. If it's a tie or the candidates split the votes and no one has over half the votes, then I can declare anyone the winner. It's chaos, right? Maybe someone gets lucky. Maybe I don't do anything. But if someone is a winner, I want to definitely return that person, right? I want to know that. And so this algorithm is going to work. So why is this going to work? Why is this guaranteed to satisfy this property? Yep.
Because we learned about this algorithm in the algorithms class.
Suresh is teaching this in the algorithms class? Okay, cool. Well, all right, so what did you learn from Suresh why this works?
There's proof for that.
Okay. Yeah?
Well, if it occurs more than half, it's got to be consecutive at least once.
Well, it could be there are like 21 things, and all the odd ones are, so there'd be 11 odd ones, and they'd all be that element, but the even ones are not. So it's a little tricky to get.
Oh, I was just going to say, when we get to, like, if you think about it, we can kind of split it up into cases. So, like, in one case, we get to the C equals 1, and we need an element that's not, like, a majority element. We say that that's our element, but then we have to, like, get enough of it to, increment back up to C equal to... You can kind of split up the cases.
Yeah, so you kind of...
You want to like look at the case, but you have to go over the majority.
Yeah, so you're kind of on the right track. So here's some intuition, and then I'll make it a little bit more precise, but I'll stop a little bit short of doing a formal proof. So if you do have something that's in your counter, and that thing is going to be the majority, at least the majority of the remaining elements, right? If it's the majority of the remaining elements that's already in your counter, then you're going to have more increments than you're going to have decrements. Right? You're going to have more times you increased it in this step than you had times where you decreased it. So it's going to still be in your counter at the end. If something has the majority of the remaining elements, or the majority of all the elements, then at some point it will need to be in your counter. Because you're going to have more things where you decrement a different counter than such that then there are other things. So you can only add something with a different label less than m over 2 times. And for each of those, you're going to have something where you're decrementing it because you see the true majority label. Okay, so a different way to think about is you have going to have these two bins. Right? And so let's say that this is the true majority thing, and this is all else. And the worst case is when there's only one other object. That's the most interesting case. Otherwise, you're going to cancel each other out and only help the guy in the majority. And so every time you have one of these, you throw a ball in this bucket. And if this is the counter, if the label is on here, then you're just going to keep throwing these balls in, and you're going to build up this stuff. And if it's majority, every time you see something else, you're going to either take a ball out, or if these balls get empty, then only at that point do you start. Only if it's empty do you start putting balls in this bucket, right? And so every step you're either adding a ball in this bucket or taking a ball out of this bucket, where this is the true majority. And you're going to have more of putting ones in here than taking these out. And instead of doing that, you can just keep track of, let's say you had 2 counters, right? And you look at the counters of the majority and the ones of everything else, and you know that each of these, I should have either taken one out from here if it was a red ball, or taken a red ball out if it was a blue ball and I had the counter in there. And so if I had it doesn't, I just care about the relative difference of these, and I know at the end this one will always be higher, so there'll always be at least one blue ball in the bucket. And that means I'll always have this label if there is a majority. Okay, so maybe you didn't follow all the steps, and maybe I didn't formalize all the details, but hopefully you can kind of see that this is going to work. Right? But this is a pretty weak property. Only if something is over half of the elements can I actually guarantee I find it. Okay? But if we went back here, right, for this heavy hitter problem, I wanted to, if this phi was 1/2, I'd be in pretty good shape. Right? I kind of would have something, but that's not the interesting case. It's interesting when phi is like 5%. So I need to somehow generalize this algorithm to win, to do something better than just a 1/2 here to this majority. Right? So what can I do to do a little bit better? Yep.
More counters.
Yeah, I can add more counters. I had this silly restriction. I can only use 1 counter and 1 label. What if I used some k counters? So what if I used 10 or 100 counters? How well can I do? Well, how would I change this algorithm here? So let's say that I used k counters and k labels. So how would I change this? So let's say that the first, the simple thing is the first k. So I can say if I have a label that's not used and I see something new, I can use the label, right? So for the first k, use new label, and so I'll set L, let's say call this LS equals to AI if it's new, and the counter S is equal to 1. So if I see something new, I'll just use a new label and a new counter, right? So I can do this until I've used them all up when I see something new, right? So now this is kind of the internal loop of the algorithm. So now I have like a for loop over the rest of the items in my stream. And so I say if my AI is equal to some LS, so I can check all of them, I can have a hash table, I can do something. If it's equal to some of these LS's, then I'm going to increment the associated label, the associated counter. So if I match one of the labels, I can increment the counter. So else, let's see, if some CS equals to 1, then I'm going to do something. So it's if some CS is trying to write this concisely. I've got it written in kind of more excruciating detail in the notes, but if all CS is greater, let's just say, is greater than 1, okay? If greater than 1, I need to do something, and then else. So if at least one of them is less than 1, then some CS is equal to 1. Then in this case, again, I'm going to set the label to be AI and this particular label and this counter equals to 1, right? So if one of the counters is somehow low enough, right, then I'm going to I'm going to take over this label with the new thing I've seen. But what happens if all of the counters are big, right? So before, if I only have one counter, and if it was too big, I decremented that counter. What happens if all of the counters are too big? What should I do at that point?
Decrement all of them.
Yeah, so there's this weird, there are actually a couple things you can do that work, but what you want to do, the simplest way is to, let me just say, for all counters, CS equals to CS minus 1. So I'm going to shrink all of the counters now, okay? And then I actually don't need this else. I can make, and then I have this if statement. If some counter is equal to 0, then I'm going to reset this. Okay, so if after I decremented all of the counters, one of them is equal to 0, then I'm going to take over this counter with this new item. Turns out I don't even need to take over it. I can just not do anything. You can do different things with the bookkeeping and still see that it works. But if I'm going to decrement all of the counters. Okay, so this seems kind of strong to do. Let's say I have 100 counters and I see something new. I have to shrink all of them. Right? This seems kind of painful. But this piece of bookkeeping right here, where I shrink all of the counters, is what ensures that this actually works. Okay, so first of all, I've got some like pseudocode up there that's a little bit of a mess. Sorry, but is anyone unclear on this? It's a really simple algorithm. So everyone's, if I ask you to implement this for homework 4, you could do this. Yeah? Okay. So now why does this work? So what I'm gonna guarantee is should have saved space on the slide. Okay. So so let's. Why is this algorithm working? Let me copy this back over. So if AI equals some ls, then I'm going to do CS plus plus this associate counter. Else, if all I don't even need this. Else, well, I need if, yeah, so if all CS is greater than 1, I think it's greater or equal than 1, then I'm going to do, for all S in K, we're going to do CS minus minus. And so then if some CS equals to 0, then I'm going to set LS equals to AI. Okay, and I can keep, it's okay to keep the counter at 0 in this case. Or I can set this counter CS equals to 1. Okay, so this is the algorithm. This algorithm was proposed by Mishra and Gries in 1982, before people even thought about streaming very much, actually. And it's been rediscovered like 4 times. It's a really kind of simple, and even though this step of decrementing all of them, it seems a little weird, it got rediscovered a bunch of times. It's an obvious enough thing to try. So why does this work? So the bounds I'm going to get, I'm going to claim that at the end, I'm going to say that all fj are going to be greater than my fj hat. Yeah, so I'm actually going to get, I'm not just going to solve the heavy hitters, I'm going to solve this frequency approximation algorithm. So it's going to be greater than this plus m over k, which will be greater than f of j. Well, yeah, okay, so it'll be greater than the true, than the, okay, so I'm going to get this property. This is the true count for every value j, right? And this is my approximate count. And I'm going to be able to, for every counter, I'm going to be able to tell you an approximate count f of j hat. For every IP address, I'm going to say it's going to be no bigger than the true number of times I've seen that IP address, and no, and it's going to be, should be minus. And it's not going to be too much smaller than this, okay? It's not going to be too much smaller. If I take this and I subtracted minus k, k over m, it should be m over k. Okay, so who's, I'm glad at least one of us is paying attention. Okay, so this is the number of all things you've seen, and this is the number of counters you have. So as the more counters increases, this is your error term, and we can set like epsilon equals to 1 over k. So as the number of counters increases, your error decreases. So if I want to get 1% error, I need 100 counters. Okay, so I'm going to claim that to get 1% error, and it's always going to be an undercount. I'm never going to estimate too many. Then I'm going to need 100 counters for that. So this is my claim. Okay, so, and that means that's for any value j. That's even though I'm only keeping k counters. How can I do that? How can I, this is for all IP addresses. How can I do that with only 100 counters? Why is that possible? How would I, what happens if I ask you, I ran this data structure and I keep 100 counters and I give you an IP address which is not in one of my labels?
The rest are all 0, but that's still within the bound.
Yeah, right. So if something, so f of j hat equals, is equal to cs if ls equals to j and it's 0 otherwise. So if I go with my query j and I say, does this equal to a label? If it equals a label, I return the counter. If it doesn't equal anything, I return 0. And that's going to be okay because if I took the true count and I subtracted this value here will be less than 0. I claim that if I don't have it in a counter, then the true count minus m over k will be less than 0. So I don't have to worry about it. Right? Okay, so and this is going to be that works similarly to if I have, okay, so the reason this works is going to be similar to this majority algorithm, but now I just have more of these counters, right? the kind of the key insight here, why this works, is what is the total number of times that I can call this step? How many times can I call this step here? I'm going to bound the number of calls to the step where I decrement all of the counters.
Less than 1 over k.
Less than what?
1 over k.
Well, less than 1 over k is less than 1, but you probably mean less than m over k. So yeah, so I'm going to call this I'm going to call this step here less than m over k times. So call less than or equal to m over k times. Okay? So what it means is that every time I'm through here, I'm always going to put, so I can think of always putting something in a counter, and think of if I didn't have space, I kind of put my element into some extra dummy counter, and then I decremented it. So I can always put something into a counter, and then I can only decrement it. But if I have one of the counters which is empty, I don't need to do this decrement. And so every time I do the decrement, I'm decreasing the total count of the things I have by k. So if there are only m things total, I can only decrement the total count by k, m over k times. Right? Can only, boy, that was, how many times do you spell only wrong? Can only decrement all k counters m over k times, since k times m over k equals m, right? Otherwise, I wouldn't have something to decrement. And because that's the only time I ever decrease any of the counters. So I only decrease them if I call this, and so no counter is decreased more than m over k. So at the end, if I have something in there, it has to be, if it was above this threshold m over k, then I would have had something in there, and I would have had a good count. If it was below that, I might have something in there, I might not. Depends on when I saw it. So that's kind of how you can get this property. So I can approximate all the frequencies with a small number of counters. All right, so that kind of makes sense. So it's it's a really cute trick for counting. Okay, so this is really easy to implement, and it works pretty well. There's a couple of different ways. There's a different way called the space-saving algorithms, which sometimes works a little bit better. You never do any decrements, but if you get something, so instead you never have this thing where a counter is 0. But if you see something and you don't have room for it, what you do is you take the thing with the smallest counter and you swap its label to the new thing. And you increment the label by 1. So you always keep the total right number of counts, but the smallest label sometimes gets swapped. And doing this also works. This gives you an overcount instead of an undercount for all of them, but it's still bounded by m over k. And often in practice, this can kind of, it depends whether you want an undercount or an overcount. It more consistently gives the heavy counts to be more accurate. So it's probably even a little bit less intuitive that you do this label swap, but basically just as easy to implement. Okay, so I'm going to talk about one other kind of a fairly completely different way of solving the same problem now. And this is going to use hashing and randomized approaches. So this is going to be called a count min sketch. And so this is indicative of a kind of a class of these streaming and small space summary algorithms called sketches. And the idea is you have some data A, and you're going to apply some matrix. Now you're not actually going to be applying a matrix doing matrix multiplication, But you can model it as multiplying it by a random matrix. This matrix elements are going to be random somehow, and the output is going to be a small sketch, say B. Okay, and this B will be much smaller than A. So this the dimensions need to line up in some way. But this is going to have some, so we're not going to think about it this way in general. We're going to think about it kind of procedurally, algorithmically. But this means that as I do updates to A, I just have to pass it through whatever described this S matrix, which is really the algorithm. But I can pass updates through and update my sketch. Means if I realized I made a mistake, I can go and fix it. If I added something and I want to delete it later, I can go and delete it. Whereas this previous algorithm, if I wanted to delete something, I don't know how to update the sketch I have while maintaining the guarantee. In particular, the problem case is you put in like a million things, and then you take almost all of them out except for one thing that occurred once. And now you want some guarantees that have to do with how many things are left in the sketch, and that's hard to make guarantees. You have to to get some guarantees like that, you have to use some version of algorithm that you can think of like some random matrix you're projecting onto. Okay, so this might seem kind of strange, and you need to see a lot more of these types of algorithms for this idea to make sense. But let's see it kind of procedurally, and maybe you'll understand what this looks like. We'll see. And we'll kind of come back to this a little bit when we talk about large matrices again. Okay, so the idea here is you're going to use a hash function, and this is going to be a random hash function. Okay, and this is going to be, we'll call this H, and it's going to map everything in your domain, I guess this was N, sorry, into a smaller domain K. So it's random, so that means that essentially it's going to map each object into a random spot, a random number 1 through K. Okay, so we're going to think of this as the data is coming in, AI, and it's going to map onto this table. And inside of each of these tables, you're going to have a counter, C1, C2, C3. This will be we'll call this CJ up to CK. And I have K counters now, right? Okay, so just think of this like a hash table, but I'm going to have counters instead of just storing stuff. Now, I'm not going to keep track of which things I put in here. I'm just going to keep a counter. Okay, so this is pretty simple basic idea, right? I just keep this, again, maybe a pretty obvious idea too, right? So how well does this work? So just using one hash function is not going to work that well. I'm going to need to use I need to use a set of these hash functions. I need to go up to H1, H2, up to HT. So I'm going to use T hash functions. And so instead of getting one table here, I'm going to get T of these tables. Right? So if this is hash S, it's going to map to, I'm going to have a counter in here too. So this will be C1S. Right, so let's blow this guy up here. So this would be CJS. So I'm going to have a counter in here. And so for every item that comes in, I'm going to apply all T hash functions and map it to one spot in each row. So for every row, it gets mapped to one of the counters, and I increment that counter. Okay, so I'm going to replicate this idea of just counting at a simple random hash, and I'm going to do this T different times. Okay, so this is all I do to store the data. I need to do a little bit more work to get the data out. now that I've stored the data in here, you know, so the algorithm for storing is simple. How do I get some value f of j hat out of here? How would I retrieve for some value j? I want to estimate the frequency. How would I do that? So if I only had one hash function, how would I do that? Yeah. Yeah, so I'm going to do something where I'm going to look at the counter, and we'll call this, we'll index this as s. So if this was s was equal to 1, I'm going to look at the cell by looking at hash function s of j. Right? So I'm going to hash this j. I'm going to say hash of j, hash of 1 of j is going to point to this cell here, and then I'm just going to read this counter. So this counter of hash function s at value j. So I found this counter and I read it off. Okay. But if I have multiple counters, then which one should I use, or how should I use all of them?
You should use the smallest one.
Yeah, I should use the smallest, right? So I'm going to return the min of s equals s in this range t of all these possible counters. That's why it's called the count min sketch. I'm counting, and then I'm going to take the minimum of all the counters. Okay? Because they're all going to be overcounts, right? I'm going to, for everything that comes in, I'm going to keep track of what went in there. But sometimes I'm going to hash other objects into this location too. And so I'm going to count those as well. So every one of these will be an overcount. So I'm going to have the property, so it'll be pretty clear that fj hat should be greater or equal than the true count. And what I want is that fj minus, say, something like epsilon m is going to be, or plus epsilon m is going to be greater than my approximate count. Right? So if I take the true count and I add epsilon m, it should be. I want this to be greater. I don't want it to be too much smaller. I don't want the approximate count to be too much greater than the true count. Okay. Okay. So in order to so I'm going to take the minimum because it's always an overcount, and the smallest is going to be the least overcount by definition. It's going to be the best approximation is the smallest one. Okay, and so I'm going to have k counters. So k, I'm going to do this by setting this now to be 2 over epsilon. Right? Before, for the Misha-Gries algorithm, before I set the number of counters I had to be 1 over epsilon. Now I need 2 over epsilon. And I also need these hash functions, these t hash functions. And we'll set t is going to be something like is the natural log of 1 over delta. And I'm going to have some delta probability of failure, meaning this is going to hold, this property holds with probability at least 1 minus delta. So I can set this delta to be, say, something pretty small. If you do like 10 hash functions is usually enough. So you can set epsilon to be this and maybe use 10 hash functions, and you get, and so the error goes down, the probability of failure goes down exponentially with the number of hash functions you have.
Epsilon is the probability.
So, yeah, so the delta is the probability of error. So the more hash functions, the less likely I have too much error. The epsilon is going to be how accurate it is. So epsilon is the accuracy parameter. And delta is kind of the confidence that you have this accuracy. So the more confidence you want to use more hash functions. The more precision or accuracy you want to use more of the bins and more counters. Right, and so each counter takes the log log m space basically, and the hash functions they roughly take about log that you can do them in roughly log n space. You need to store something for the hash functions, and if you use something like this multiplicative hash, you can or there are different techniques you can use. It gets a bit complicated to get the best bounds for this, but you can do it in basically each hash function is in log is in log n space roughly. All right, so let's, about 10 minutes left, so let's kind of try and see why this works. Why would I get this bound with this probability? How would I bound that? Okay, so let's look at the so let's say that this counter, so let's look at counter CJS, and let's set up a random variable YJS. And so this is going to be the overcount of YJS. Instead of the overcount, you can think of just the count in YJS. Might be a little cleaner. But it turns out the ones you're going to look for are probably going to be large, so you only care about the ones that are not the ones you're looking for, and that'll make this smaller. But so you want this to be is the count in this counter. What is the expected total count in here? So you can say that because these are random hash functions, okay, let's define this. No, this is the overcount. This is actually the count. I'll break this down into two steps so it'll match the notes a bit better. So this is the count in this object. This is going to be messy. Okay, so the count in this counter JS, and so the S isn't really going to matter so much. So from frequency Fj. So I'm going to look at this particular counter. So this is the jth counter, and we'll only consider one of the rows at a time. So it's the jth counter, I guess, from object F. I'm overloading I, so let's call this from object I. Let me draw this better. Okay, so we'll say that y ij is going to be equal to the count from object I in counter j. Okay, and so this will be equal to f of j with probability 1 over k and 0 otherwise. Okay, so with probability 1 over k, if I don't know what this object I is, with probably 1 over k, this is fi. Okay, with probably 1 over k, it's going to hash to this counter, and it's going to have an effect of frequency I, because that's the frequency of this object. Right, so I know that the expected value of yij is equals to fj over k. Okay, so the expected count here is fj over k. In this counter, based on the fi over k, based on the ith item. Okay, and so if I add this up over all items, I can say xj is going to be the count in counter j. Then this is going to be the sum over I in n of yij. And so then I can say that the expected value, what is this? There we go, of xj is equal to exactly the sum over I of these fi over k, which is going to be m over k. Okay, so this is looking like a term that we want, m over k. the expected count in any of these counters is m over k. Maybe this is kind of obvious, right? But that means it's independent of the distribution of how the data is laid out. So the expected value is m over k. But it's random. All we know is the expected value, and it's greater than 0. So in order to say that, now this k was 2 over epsilon, so that means I got m epsilon over 2 is the expected overcount. So if you're happy with the expected overcount, then that means you already have a bound. I expect that the overcount is going to be, epsilon over 2 times m, which is already good. But I want to say that it's what's a very small probability is it more than epsilon over m, epsilon m over 2, right? So epsilon m instead of epsilon m over 2. And there's a technique you can use that's called the Markov inequality. So that says that the probability that any random variable, so let's say I have a random variable x that's greater than a, the probability x is that is always greater than 0. The probability it's greater than a is equal to the expected value of x over a. Or is this probability is less than expected value over a. Okay, and this is kind of a neat property. I know it's greater than 0. So what that means is that if I draw some distribution, and this is 0, I know it looks this some probability distribution like this. I know the expected value of x is here. And if I pick some point A, then the probability it's greater than A is small. It's going to decrease. The larger I make A, the smaller this probability, and depends on the expected value. And the reason this is true is that if I put too much probability out here, the expected value would have to be larger. So I can't put too much probability out here, otherwise it would actually make the expected value to be bigger. So basically, if I have a bound in the expected value, then I can say it can't be too much larger than the expected value. So what I'm going to use this using A as being epsilon over 2. Or I'll use this as being epsilon m. So I know the expected value is, or I'll use this as being, so I'll set A, if I set A equals to epsilon m, then the probability that this xj is greater than epsilon m, which is what I want here, that the overcount is greater than epsilon m, is going to be less than the expected value, which will be epsilon m over 2 divided by epsilon m, and this is 1/2. Okay, so the probability that it's greater than epsilon m, which is the bound I wanted here, is going to be less than 1/2 probability. So less than half the time will I exceed this bound. Okay, so this 1/2 is not, it happens every time I flip a coin. That's not that great, but that was only for one of these counters. That was only for, or one of the hash functions here. So that's why I use t of these hash functions, right? They're all independent. So I'm taking the minimum of these, right? So remember, this was, if you can spot the algorithm in my mess of a slide up here, if you can, I took the minimum. So that means if the minimum was greater than epsilon m, that means all of these hash functions had to have had this happen to them. All of them had to have gone the wrong way. All of them had to have been out in this tail. I'm saying that this probability, for all of them, it has to be small. These are all independent hash functions, so that means that if they all failed, that happens with probability, the probability that the min xj is greater than epsilon m is less than 1 over 2 to the t, because I have t hash functions. They're independent, so I can decrease this. I can take the product of all of these probabilities. They'd all have to be bad. And so now this goes down exponentially with the number of hash functions. And so if I say the probability bad with log 1 over delta hash functions, that means that it's probability delta. If I plug the log of 1 over delta in here, you get that this equals delta. So with t hash functions, log over 1 over delta hash functions, I get a delta probability of error. So I can set that as small as I want. Yeah?
Is this inequality true irrespective of the probability distribution?
Yeah, as long as you need that the value needs to be greater than 0 for all values, then this is true. So this is a pretty weak, but it's incredibly general. All you need is the expected value. The Chernoff bounds I talked about earlier in the class, they needed much more information about how you got the distribution. And there's something in between that's called the Chebyshev inequality that you can use just on the expected value and the variance. If you know those, you can get a slightly stronger bound. But for the count min sketch, all you need is the bound and the expected value to get this. Yeah. Okay, cool. So this is, again, a very simple algorithm, but it gives you this summary of these counts. So we'll talk about counting more complex things on Wednesday, and then we'll kind of see how to do some more interesting things with these sorts of summaries when we get to the dealing with the regression and thinking about data stored as matrices. And you can apply these to do some even cooler stuff.